Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to take a look on the simplified approach that Autodesk Robot uses to calculate seismic loads. So to start with, I am going to select my 3D building design. Now, it's worth it to notice that I am going to heavily reference the ESCE code, which is an American standard used for calculating seismic loads. For other standards, you have to refer to your own codes to understand the different topics and the different terminology used there. So before I start, of course, I will have to set my parameters and make sure all my codes are correct. Now, this was explained before in a video talking about job preferences. It's linked above. Now I'm just going to go to my job preferences, go to my design codes, select the load codes, and make sure that my seismic loads are under the ESCE 7. Now I'm using the 2016 code. Of course, you can switch to any code you want. I'll be sticking to my ESCE code. Alright, fantastic. So I will start with this very simple structure and grow up to a multi-story building. Of course, all of this is simplified because the objective of this video is to basically introduce the topic because it will be used later when I have the bigger projects to be done here. Alright, fantastic. So to start with, I'm going to select my grid system and I'm going to just make me a small room that is 5 meters by 4 meters, just a small room, nothing special. And the height of the room is 3 meters, which is the story height. Of course, you can change the story heights from the story command. This was covered in the building video that is linked above. I'll apply that. You can see that I have my room defined. Please notice that my goal in this video is not to design the structure nor to dimension it. It's just to model earthquakes because this is the first video, so I need to keep it as simple as possible. So I'm going to select my reinforced concrete columns. I'm just going to select me a 350 by 700 column. Now it might be oversized, but I don't care because my goal is just to show you the idea. So the height of the column is 3 meters. It's going down. So if I start clicking here, you can see that my columns are being drawn. Now on top of the columns, I need my beams. So I'm just gonna assume a reinforced concrete beam with a section of 350 multiplied by 500. I'm not changing that. Once again, my goal here is not to size the elements, it's just to model the thing. Finally, I'm going to go to geometry, use a cladding, and select me a two-way cladding, and basically draw it as follows. And I'm going to define me two load cases. I'm going to define me a dead load case, which will implement the self-weight. And I'm going to define me a live load case, which doesn't implement the self-weight. Now in the dead load case, I'm going to just assume me some dead load. I go to surface load, planar uniform load. Of course, the explanation of all those force types was done in a previous video, so please refer to previous videos that are linked above for further detail. So I'm just going to go to my surface load, select me a basically uniform surface load, dead load. I'm going to assume, I'm going to assume that this is maybe 7 kilonewton meter square. Of course, I'm not calculating anything. My goal here is just to model basically seismic loads. So I'm applying a dead load. In the live load, I'm going to apply me a 3 kilonewton force going downwards. I think my dead load is too small. Well, I just realized my dead load might be too small, so I'm going to change it very quickly by going to the load table, to the dead load. It's 7. I'm going to put it to 10 just because I have a bad feeling about having 7. Of course, you need to calculate it yourself. Fantastic. I have my dead load as assumed. I have my live load as assumed. If you run the analysis now, well, everything seems to be alright. I didn't do any releases, so this is a framed structure. And if you open your results, diagrams and members, open the moment Y, you can see that all my beams are loaded and all my columns are loaded exactly as I am expecting this to be. Notice I'm using frames, there are no releases, but it's not today. We are not discussing exactly the modeling of rooms because we are discussing actually the calculation of seismic loads. Fantastic. So today we are going to analyze seismic loads using a simplified version, which is the ESCE code. So Robot is going to use a code to calculate the shear forces or the horizontal forces that are resulting from having an earthquake. So to do that, you go to something called calculation options, or you go to basically analysis types, and you can all see that Well, this is basically the controller that controls the analysis in Autodesk Robot. Now, I've talked about this before when we had the problem of the structural model, and this was explained in a video linked above, which was about modeling hangars. Now, today we're going to take a look on the analysis types. There is a plethora of details to be explained here, and I cannot explain everything just in one video. So for today, we want to define our seismic loads. Now, to define a seismic case, we are going to click on New, basically to denounce to robot that we are going to analyze something new. Now, there are some options here. We want you to make a seismic calculation, but this time we want it to be equivalent lateral force method. This is a simplified method stipulated by the ASCE code and other codes. Of course, this method must have its limitations that, for example, the height of the building is not more than 70 meters or something. Of course, please check out your own codes to see what the recommendations and what the limitations are. So now if you click on seismic, now a big window opens, and here is where the fun starts. Alright, so the first thing I want to say is that this window is actually the same for all the codes. So even if you are a Eurocode or rich code user, you will see the same window. Now this window defines what the code is used to calculate the seismic loads. Of course, it's the ASCE code, the code I am using. We are going to use an approximate method, which is basically that this robot is going to use the code equations to calculate the base shear and then distribute the base shear among the stories. A very important hint that just came to my mind is I am going to rely heavily on seismic terminology and jargon. So if you are unaware of base shear, short-term design, resonance, importance factors, and whatever, if you are unaware and unfamiliar with those terminologies, you should double check your earthquake design course, or just stick around, maybe you will learn those terminologies. Alright, so I'm going to use the approximate method. In all codes, usually there is a precise method which will use your model analysis, and an approximate method which uses an equivalent force. I'll come to that. I'll explain what the approximate method is. Now, for the directions and combinations, I want both directions to be loaded because I want the analysis of earthquakes to be done in the x-axis and in the y-axis because, well, you don't know how the earthquake comes. Maybe the earthquake shakes the building from left to right or from up to down, so you want those cases to be here. Now, you can define eccentricities. And what's the point of this? I need to be a little bit theoretical here. So before I continue, I want to explain to you why earthquakes cause loads. The idea of seismic loads is basically according to Newton's laws. So if you have a mass M, let's say, then there is a mutual relationship between the force and the acceleration, meaning if you apply a force, then an acceleration is imminent. And if there is an acceleration, then there must be a force that caused it, be it inertial forces or external forces. Now our structures have masses, and those masses are usually like this, fixed to the ground. And what happens when an earthquake strikes is that the ground shakes back and forth, and the mass tries to follow the ground, and that's the reason why the buildings are shaking back and forth. Now, shaking back and forth means that my mass accelerates to the right, stops, and then accelerates to the left, stops, and then accelerates to the right, and so on. Now, this acceleration and stopping actually is causing, now this is very technical because, well, you need to study earthquake engineering, but in the end, the inertial forces caused by this back and forth acceleration, m multiplied by a, is what causes your loads on your structure. And the ASCE code here has one job only. It tries basically to say F equals something multiplied by the weight of the structure. Now the weight of the structure is m multiplied by g, I know, but well, I mean from Newton's law we know that F equals ma, so you can notice that the ASCE code tries to approximate a factor that has something to do with the acceleration and something to do with the acceleration of gravity. So yeah, the sole purpose of this code of the ASCE code in this regard is to calculate this factor. And if we calculate this factor, we multiply with the factor by W. This factor is called CS and is referred to as the seismic response coefficient. Now, this equation is found in the ASCE code under the section 12.8-1 if you have the ASCE 2016 code. And the equation here for CS is also defined in 12.8.1.1. Now this is highly technical, but I only want to give you the gist of it. This CS is actually SDS, it's a factor I will just explain in a moment, SDS divided by something called R over the importance factor I. Now what is SDS? SDS is the design spectre response acceleration, R is the response modification factor, and I is the importance factor. Now, in a nutshell, because I don't want this to become a seismic lecture, although I will be starting lectures in the future once this channel reaches 1,000 subscribers, but for now, I don't want this to become a lecture. So what I'm trying to say here is that this SDS, which is your response acceleration, spectral response acceleration parameter, has to do with a plethora of things. It has to do with, first of all, the location. Well, in locations prone to earthquakes have larger factors. It has to do with the soil or the class, the soil class or the location class, and it has to do with other things. So the second thing that needs to be noticed is that those codes actually not only calculate something called the base shear, but calculate also the force distribution. So when you finish calculating using this CS multiplied by W, you are getting a base shear, meaning the equivalent force of earthquake that is hitting the base of the structure. Now your structure doesn't have only one mass. Your structure actually has a multitude of masses because you have multiple stories. You have the ground floor, you have the first floor, you have the second floor, and so on. So, I mean, for example, if you have two masses now, the force here that is hitting the base must be redistributed to each of those stories. And this is done by considering the height of a story and the weight of the story. And this should make sense because, I mean, imagine yourself holding a stick in your hand, and if you tie a 1 kilogram weight on that stick and swing it around, and then tie a 5 kilogram weight to the stick and swing it around, the 5 kilogram stick is going to take more force from you than the 1 kilogram stick. So mass is a factor. The second factor is, well, if you use the stick for 1 kilogram and then use another shorter stick for 1 kilogram, the shorter stick is easier to basically move around. So both the mass and the height, or basically the distance of the mass, is a factor in distributing those loads in the vertical direction. Finally, there is a horizontal distribution that depends on the stiffness of the resisting elements. This is really technical and, well, requires at least 4 to 5 lectures to explain. For now, I just rely on you having knowledge in earthquake engineering to understand what I'm trying to say. Furthermore, the design codes usually, I mean, if I'm drawing a plan view now, assume that this is the plan view of your floor. If you have a plan view of your structure, well, usually the mass of that floor is in the center of gravity of the shape, which is basically the center here. Now, this is true for homogeneous shapes, but in reality, the center of mass is actually not the center of area, because, I mean, the distribution of loads and weights on that slab is impossible to be uniform. Like you have here your couch, you have here your kitchen, maybe you have here nothing, just an empty room. So usually the weights are not distributed perfectly symmetric, which means that the center of mass, which is basically also the center of the applied force, is going to be shifted on one of those axes or even two. And the codes, some codes, require you to apply something called the accidental eccentricity when you calculate a force, which means that not only will the earthquake move the structure back and forth, but it will also twist it counterclockwise and clockwise. And this is really a lot of technical stuff. I will leave it as is. The only thing I want to tell you is that we are going to consider eccentricities in all directions with an eccentricity factor of 5%, meaning if the structure is 100 meters long, then the force is going to be shifted in the positive 5 meters and negative 5 meters. This is relative. Of course, you can make absolute, which means distances. Now, going back to our point here in the seismic analysis parameters, if you click right now, this is where the codes will be different from each other. And if you click here, you can see that you have the ASCE 716 parameters. You can, of course, change this to the Eurocode. Then you have different parameters. They are like A, G, and Q. Now, I am totally not aware of those parameters, I'm sorry. But let's go to the ASCE, the code that I am familiar with. So, well, if you click on the seismic parameters, now it's not an auxiliary case because you use this case to design. You can name the case any case you want. I'm just going to leave it as ASCE 716. And the CT here is depending on what type of structure you have. I have a reinforced concrete frame because I didn't actually release any of the column beam connections. I'm going to assume a site class of C. Now, it's really theoretical. It's really technical here. You need to open the catalog of ASCE and understand what a site class C is. There is soil classifications involved with that. For S1, this is the spectral response acceleration parameter at a period of 1 second, and SS is at a short period. Now those are taken from seismic maps if available. I'll assume this is to be 0.402, and this to be, I don't know, I'll just assume something like 5 or something. TL here is the long period transition period. First of all, a vibration period is the time required for a vibration element to go back and forth and back again, meaning to get back to from where it started. Now, there is something called the long period transition period, which means like it's really technical, but it means that the time required to transit from the long period domain to the short period domain. Of course, this is highly technical. I really advise you to double check the ASCE code. I just leave it as 2 seconds. R is a factor that is corresponding to the type of structure, and there is a table that decides this. This is called the response modification factor, and you can find those factors in the table 12.2-1 in the ASCE code, which actually tells you what kind of structural system you have and gives you the corresponding response modification factor. I will assume it to be 8. Of course, you need to open the code and open the table to see that. I is the importance factor. And there are in the ASCE code multiple importance factors. If you go to table 1.5-2, you have an importance factor for snow, importance factor for thickness, for wind, and for E for earthquake. And of course, we're going to need the earthquake. And now you need to define what kind of risk category your structure is. I'm just going to assume it's risk category 2. Of course, each risk category has a meaning, and you have to understand those. I'll just assume it's risk category 2. If I click on OK now, it will of course tell me that it will add some stuff. If you click on OK again, it will apply the cases. And you can see that you have the ASCE direction X, direction Y, direction X with negative eccentricity, direction Y with negative X eccentricity, direction X with positive X eccentricity, Y with, and you can see it's a combination of all eccentricities. So if you run the calculations now, this is where things get really interesting, because you have a lot of things to talk about here. Now I've run the analysis and you can see all those cases. Let's open the loads. So, well, this is my dead load, this is my live load, and this is my direction X earthquake. Now I cannot see it, but I want to see it. To see the force, you right click, go to display or hit the VV button, go to your loads and ask it to open the forces generated automatically. If you click on apply now, you can see 4 forces, 1.95 on each of them, which means that Autodesk Robot calculated the base shear, distributed it to the stories, and then distributed it horizontally to all of those columns. Now, since the columns have the same stiffness, because they have the same cross-section, all the columns got the same load. This would be different if, for example, the columns have different stiffnesses. For example, if I assume a very simple stiffness, let me just assume a dummy column, like 10 millimeters by 10 millimeters. I know this is a ridiculous cross-section, but just bear with me for a moment. So I'm assuming a ridiculous small cross-section. I'm going to apply this to this. You can see that, well, those small columns got a much smaller load than those bigger columns. Now, the reason why this is still significant, 1.2, is because even if the cross-section is small, you have the stiffnesses of the beams that correspond also to the load distribution of the horizontal forces. So, I mean, you can see the point I'm trying to make here is that your forces change according to the stiffness of the cross-section of the column. So let's get back to the point. Let's put them back to be equalish. And since all the cross-sections are equal now, if you run the analysis, you would get the same force everywhere. All right, so going on, in the y direction, you have the force in y. With eccentricity x has nothing. But y eccentricity x has something. Now what you see here is, if you go to top, let me just remove this cross sections, and this too I want to see. Yeah. So you see you have two forces on the right side that are less than two forces on the left side. The reason behind this is, well, look at this. It's direction y, eccentricity negative x. So this is my y direction. Eccentricity negative x means that my force is not exactly in the center. It's actually shifted to the negative x to the left side. Since the force is shifted to the negative x to the left side, the loads, the columns on the left side are going to be more loaded than the columns on the right side. This is the exact opposite. If you take y positive x, you see that the positive side gets more loaded. And well, you can check out all those things yourself if you want that. So yeah, I mean, Autodesk Robot is able to calculate the earthquake loads based on the simplified method. Now, I told you before that force-based shear equals CS multiplied by W. And you would think, what is W? W, you might think, is the self-weight of the structure, and you are partially right. W, as a matter of fact, is not only the self-weight, but it's the self-weight and the dead load, meaning all the loads that are not expected to move. Now, in some codes, you will have to even include parts of the live load in your earthquake calculation. Now, what's the idea behind that? I mean, technically speaking, I understand that W is the dead load and the self-weight, because when a structure is going to start vibrating, those loads, dead loads, and weights are going to be included in the mass that vibrates. But why include live load? You include live load because when the structure starts vibrating during the events of an earthquake, well, usually there are some people inside the structure, and those people have masses, and the mass is included in all the inertia forces. So some codes do require you to take parts of these live load into account when calculating your seismic loads. So to do that, you get back to analysis types, and you go to something called the load to mass conversion. So you can convert a case to become a mass. Now I want to convert my live load case, which is case number 2, to become a mass. So you click on live load. Well, you can actually select it by going to the browse button and double click like that, or you can basically type 2 here. So it's going to take my live load and take it as a mass. And of course, I told you that some codes require you to take, for example, a part of the live load, let's say 25% or 0.25. So you can actually add this case to become part of your masses of the structure. And if you run the analysis now, basically, and calculate, you can see that the numbers that were 1.95 before change. I mean, look at this. When you go back to your seismic X without eccentricity and show the forces like this, so loads, automatic loads, and open, you can see it's no longer 1.95, it's actually 2.15. The reason why it's 2.15 because suddenly the forces from live load, parts of them, are included in the forces that correspond to the W of the earthquake load. So if you have a design code that requires you to take parts of the live load into account when calculating the earthquake load, you go to load to mass conversion and change or add live load with a coefficient of 0.25 into the global mass, which will trigger a robot to actually take it into consideration. Now, to finish this video off, I'll just basically make a structure out of it, just because, remember, this is a simplified structure. I just want to go one step further and make it become a structure. So I'm just going to copy me this. Now please notice this is extremely simplified, I know, but it serves the purpose. So I'll just go like this, select this side, and basically make me copies out of it. So I'll just go to edit, move or copy, and then basically make me a, I don't know, like 4 copies out of it. I'm just going to copy it in this direction, so from here to here, and you can see that it got copied. Also, I'm going to copy it again. It's a very simplified structure, but that's the point, so I'll just copy it like this. Go to edit, move or copy, and copy it again, let's say, again 4 times. I somehow kind of love the number 4, I don't know. So I just copy it 4 times, and I have my structure. So now I'm going to copy my stories. Of course, you should not have selected anything. If you select anything before you copy stories, then only the selected gets copied. So don't select anything. Right click here, stories, copy story, and I'm gonna copy it once, twice. I go here twice, and I think I'll just copy it a third time if you want. So just copy story. Okay, and I'm gonna copy me a story here, which is gonna be my fourth time. So I just copy a story again, and now I have 4 stories. Of course, I'm gonna remove the filter of stories so that I can see the structure. I'm gonna run the analysis now, hoping that nothing explodes, but I don't think anything will explode because I didn't do any releases, so there is no stability issues. So it's done, I think. It's just checking some cases. It takes time. So now it has calculated everything. Of course, I'm gonna check out the forces on the right side or the left side. Just go to display, go to loads, ask it to show me the forces generated automatically. And well, what do you know? You see the following thing. I told you before that the height is a factor and the mass is a factor. You can see that the nodes on the higher floors have more force than the nodes on the lower floors because the height is different. Also, of course, the columns in the middle have more force than the columns on the outside. This totally makes sense, and this is perfectly fine. Fantastic. Now, what happens if you replace the claddings with shells? I will not do this. I will only do it for one cladding, so I'll just delete this and just add me one simple shell like this. Now, it's just for testing purposes. I know this is 300 millimeters, which is ridiculously high, but I'll just do it for testing purposes. Now, I added me a shell. If you run the analysis now, you will see that each node on the shell will get its own corresponding earthquake load. So if you just run the analysis and wait, you can see that each point on that shell is going to get its own little earthquake force. You can see it like this. Of course, the forces are small because, well, there are a lot of nodes. And second of all, because they didn't add any forces on the shell. But I just wanted to show you what happens if you have shells instead of claddings in earthquake calculation. And just to remind you, if you want to see the forces again, you click on display, ask it to show you the loads that were generated automatically. And of course, you can show the load values if you want, but it becomes a mess. So you can see that, well, Autodesk Robot has perfectly modeled the earthquake loads applied on a structure in a way that makes sense. So yeah, I think this ends my video. So well, I hope that you enjoyed the video and that was beneficial to you. If you have enjoyed the video, of course, please consider liking, sharing, subscribing, especially subscribing. This is the Civil Engineering Essentials channel, and we will catch you in the next video.